proprioceptors, or proprioception, is the feeling of knowing where you are in space. So these are sensory receptors that kind of give you some information to the degree, the direction, or the rate of change of your body movement. So how much is your body changing, the direction that that segment is changing in, and how fast is that changing. So if you're moving your arm around in space, and you look to the side and you don't actually see your arm moving in space, you still know how fast you're moving it. You know the direction. You know you're making a circle this way. And you know the degree of how much it's changing. How big is your circle, or how small is that circle? So it tells you that information. So without looking at it, you know what you're doing. So people like Ian Waterman don't have these. So if he were to look to the side, he can't tell if his arm is moving or not. He doesn't know what direction it's moving in. Somebody can pick up his arm and start moving it around, and he would have no idea that that's going on. So how you know the direction, the degree, and how fast you're moving is because proprioceptors are telling your brain that that's what's going on. They transmit this information to the central nervous system, so you know what's going on. And then these receptors are located in the muscles, the joint, and your skin. And we'll talk about each one of those. So this concept of the sixth sense, if you took motor learning, you talked about this in regards to Ian Waterman, IW, the man who lost his body. He lost all light touch, the feeling of touch, as well as muscle proprioception from a viral attack. He got a virus when he was like 19. And it destroyed all of these. So he was normal before he got sick. And then once he got sick, he woke up and couldn't feel anything. Complete loss of all large myelinated sensory neurons. And he lost all of this from the collarbone down. So his head still feels normal, but the rest of it doesn't. He has motor function, though. He can move himself. He just doesn't know. He can't feel when he's moving himself. So, watch that link on iLearn. It's really fascinating, if you haven't seen it already, to listen to him, to figure out how it is he had to retrain himself to move and how he does it. And when he walks, he has to look at himself. He has to look down, and he goes like this when he's walking, because otherwise he doesn't know where his feet are, right? If you turn the lights off, he falls to the ground. So the only way he knows where he is through his vision. So if he's not looking at his legs, he can't move them, basically. So he has to be able to see himself. It's really a fascinating thing to. It took him like 9 months just to learn how to sit up from his bed. So it was just a really interesting link if you have 7.5 minutes to watch. So one of the very first, the first proprioceptor we're going to talk about is muscle spindles, and some of you might have heard of these before. A muscle spindle is like a little capsule. It's like a gel cap, like those pills. That's what they look like. They're a little capsule, and they're filled with some fluid. And in the fluid is these little specialized muscle fibers. So we have little muscle fibers inside of these capsules. And we'll talk about what those are called in a minute. These are located predominantly in your muscle bellies. However, they are located throughout the entire muscle, but you have a higher concentration of them in the belly of your muscle. They are parallel to your muscle fibers, so they kind of just are sporadically located all along your muscles. You just have little parallel capsules. When these are stretched, a sensory nerve is attached to these receptors. It's one of some sensory nerve. It's going to articulate with these capsules. So when these capsules get stretched, like if you were to stretch your muscle, they send this information to your central nervous system, telling you your muscle is stretching, because otherwise you wouldn't know. So when you stretch it, it sends information up to the brain, which activates a motor neuron, causing a contraction to occur in that muscle that picked up the information of getting stretched. So let's say it's your biceps. The muscle spindles sends information up into your brain saying you've been stretched. it sends the motor neuron that's associated with those muscle fibers, sends them a motor neuron saying, contract. More spindles are located in muscles controlling precise movements. So, fine motor skills in the muscles that control segments of your body that are associated with fine or precise movements has a lot more muscle spindles, so that you always know you have a very fine control of how fast like your fingers are moving to give you precise types of movement. Does that make sense? So muscle spindles kind of look like this. So this is the normal muscle fiber. Normal muscle fiber is called extrafusal fibers. These are your regular muscle that we've talked about so far. Inside of this fluid-filled capsule is specialized muscle. They're called intrafusal fibers. They're inside the muscle spindle. The center portion here, where you see this, this is called an afferent axon. So these are like, this is like sensory information and motor information is going out to the side. So down in the center, you have sensory neurons that are here. This center portion is non-contractible, so it does not contract. However, the ends that have motor neurons associated to them do contract. And we'll talk about this specialized portion in a minute. So I want you to see in these muscle fibers, in the middle is all the sensory information. So when this gets stretched, this picks up, you've been stretched, sends the information out to the central nervous system, sends the motor neuron back down to the contractile side, which are the ends contract, and it says contract. So, there's two parts to this non-contractile portion of a muscle spindle. There's two types of sensory endings. One type of ending is known as a phasic ending, and one is a tonic ending. We'll talk about what that means in a minute. So one end of this sensory neuron is called your primary end. And the primary end has a phasic response, or a phasic type of stimulus, meaning that it responds to the velocity of change of length. So the rate of change of length. Sensitive to the velocity of the muscle change, rate of change of length. This sends sharp impulses up to the sensory, up into the central nervous system when the velocity is getting quicker. So depending on how fast you are changing the length of your muscle, these guys increase a stimulus, telling you this is how fast this muscle is changing length. Now, the second type of ending that goes to this non-contractile portion of the muscle spindle is called the flower spray ending. And they have a tonic response. So they're coiled around the end of the non-contractile midsection. So what does that mean? Versus these guys are coiled around the middle non-contractile midsection. Middle is the phasic. Outer middle is the tonic. So middle is where the phasic, the primary endings are. Just on the opposite side of them, but still in the middle non-contractile portion, is where the tonic, the flower spray responses are. The flower spray responds to static muscle length. So these are telling you more where you constantly are, and not how fast you're changing, but this is the length that you are at. Does that make sense? Do you see the difference that in those two? No? Yes? So phasic is telling you how fast you're changing. Tonic is letting you know where you are. Right? It's letting you know what length are you at. So when your arm is out here, your bicep is a certain length. The tonic is letting you know. Now, if you're going like this really, really, really fast, the phasic is letting you know how fast you're changing length. And these are telling you, you are changing length, this is where you're at. the impulses that they send is directly proportional to the length. So whatever length you're at, it has a certain impulse that goes up to the brain. So when the brain receives that impulse, it knows it's at that length. Yes? Okay. So, muscle spindles are innervated by gamma motor neurons. They stimulate the intrafusal fibers at the ends, causing them to contract and shorten the muscles. So the motor neurons are on the end, the contractile portions. When sensory information is sent up from this middle non-contractile portion up into the central nervous system, they send these gamma motor neurons, send an impulse down back, and it tells these guys to contract and shorten the muscle spindle, and all the muscles that are surrounding it. Second proprioceptor we're going to talk about, GTOs, Golgi tendon organs. These guys are embedded in series at the myotendinous junction, right? And what would we say was about this portion? Remember when we talked about how muscles connect to bone, and there's a point where the muscle and the tendon are connecting, and what did we say about this specific spot in regards to strength? Remember?
The weakest part?
It's the weakest part, right? It's the weakest part. So the weakest part, where the muscle to tendon to bone, that weakest part, we have a whole bunch of these GTOs located there. The tension that's coming from the muscle through the tendon, when that tension is increasing, GTOs get activated. So they tell your brain constantly how much force or tension is going into this muscle, into this tendon, then out through to the bone. So when this tension gets to be too much, when you're contracting your muscles too much, and these guys think that potentially you're going to tear, they send a signal up into the brain, down the motor neuron, stopping the contraction from occurring. So they tell you to stop. And then it's a reflex when you are like, let's say you have like a weight and you're losing to this weight and it's too heavy for you and you just kind of drop it. That's the GTO saying stop the contractions. So they tell you to drop it, drop the load. It's a protective mechanism. Now, I have to preface this in saying that latest research has come out that this may not actually be true, and it could be the exact opposite of this. That they actually are saying, continue to contract, but we're going with this premise, because this is the premise that we've been, for the last 100 years, this is what we thought they were doing. We may be wrong, totally, but this is what we're going to go with, okay? And until more research comes out and they've decided, no, it's the exact opposite of this. But until then, okay, so GTOs, how are they different in muscle spindles in terms of the stimuli? What's the stimulus for muscle spindles? What causes them to activate and do something? Well, contraction is the response. What stimulates them to do that? Change of length, right? Okay, so muscle length change. That's the stimulus for a muscle spindle. What's the stimulus for a GTO? Tension and force, yes. Right? So different information. They get activated with different information, okay? So we'll keep coming back and trying to figure out all these stimulus. Now, we have another one. These are called Pacinian corpuscles. They have a different stimulus. So muscle spindles, change of length. GTOs, tension or force. Pacinian corpuscles, they have a different stimulus as well.